So, well, like I said, I'm going to try to, well, start by talking in general about what set theory does very briefly, and slowly go deeper and deeper into a specific line of research that I've been involved on. So at the beginning, I guess a lot of people, I think, when they hear set theory, they think of the foundation of math, because that's probably one of the few things that gets taught in many undergraduate degrees in mathematics. So the gist of this is basically that as we progress in learning math, we learn that most mathematical objects are defined as sets equipped with some additional structure. So for example, a ring is just a set equipped with two binary operations that satisfy certain properties. A topological space is a set equipped with a family of subsets that has certain properties, and so on. So there's always this idea that mathematical objects are just sets with some additional structure. And that additional structure can also be defined in terms of sets and their elements. For example, typically, like I said, in a ring, the additional structure is a couple of binary operations. In a metric space, the additional structure is a function from the Cartesian product of the set to 0 infinity. So it's basically just functions in a topological space is directly just a family of subsets. So that's clearly a bunch of sets, but also functions can be realized as sets, or I'd like to say implemented within set theory as specific kinds of sets of ordered pairs that satisfy certain properties. So at the end of the day, you could always, every mathematical object, sort of like trace it down all the way down the rabbit hole till you get to sets, and it's all built with sets as the basic building blocks. And so, at least in theory, all of math, even though it's not set theory, could in principle be translated to the language of set theory. This is, of course, not very practical most of the time. That's why we have people working in different areas of math, and it takes them years to, well, to be able to use the modes of reasoning, arguments, and so on language of their area of research. So it's not practical to really think of any branch of math as set theory, but every now and then you have questions that turn out to require a fine analysis of this translation into set theory to be solved. So at the very bottom, we have the axioms of set theory as the final arbiters. There's various examples of this. I don't know, the one that comes to mind very recent is in the theory of C-star algebras. There's an object called the Culkin algebra, and there was a question whether it has outer automorphisms. And this question turned out to be independent from the axioms of set theory. So that's an example of a question that people working in the area were not able to solve using only their methods, but this really required a fine analysis of how to translate all these objects from functional analysis into set theory. And so that's one very important facet of set theory, but I claim that this has fundamentally two phases. And of course, one of them I just described is the foundational phase. But another thing is that set theory, I think, provides us with a framework for studying the combinatorics of infinite objects. This is in a very abstract sense. Obviously, every mathematician sometimes is concerned with infinite objects. I don't know, maybe an analyst is every now and then concerned with an infinite dimensional Hilbert space, or an algebraist every now and then has to deal with infinite rings. But in set theory, we tend to study not specific infinite objects, but the whole generality of how infinity behaves. And yeah, if someone wants to study this, the place to go is set theory. As an example of both things, of the foundational facet and the fact that this is infinite combinatorics, I'd like to tell you a brief story, the continuum hypothesis. So, well, some of you probably know this story, but it all starts with Cantor's theorem. In fact, arguably, all of set theory starts with Cantor's theorem, where he discovers that there are strictly more real numbers than natural numbers. We're talking in the sense of cardinality. So what this means is, well, first of all, that obviously the natural numbers can be put in an injection into the set of real numbers. That's clear because they're a subset. But more importantly, so this means the number of real numbers is bigger than or equal to the number of natural numbers. But more importantly, there can't be a bijection between the set of natural numbers and the set of real numbers. This is written like this, and intuitively what it means is that the set of real numbers is strictly bigger in size, in number of elements, or well, the technical term is in cardinality. And so this prompted Cantor to ask a question that would be extremely important in the story of the subject. Since the real numbers are strictly larger than the natural numbers, it became a very natural, well, and it's not only that, also many objects that you naturally define in analysis turn out to have one of these two cardinalities, to be either equipotent to the set of natural numbers or to the set of real numbers. For example, the set of continuous functions has the same cardinality as the set of real numbers. On the other hand, the set of rational numbers has the same cardinality as the set of natural numbers. And you can define various sets. The Cantor set has the same cardinality as the set of real numbers. There's many things that pop up naturally when you're studying analysis. And when one thinks about these sets that pop up naturally, it turns out that basically all of them can be eventually proved to be equipotent to one of these two sets. So it becomes a very natural question whether there's something else in the middle. Is there a set with cardinality strictly between? And so this was a question that Cantor worked a lot on. He never got to really solve it. Hilbert thought that this was an important question. So in his famous list of the problems for the 20th century, the problems that would drive the way of how math is done for the century and the problems that are important to try to solve, the very first on his list was precisely this, answer Cantor's question. And well, eventually it was solved. This is a theorem partly by Gödel, partly by Cohen. Each of them did arguably one half of the theorem, and Cohen got a Fields Medal for this result. But the answer was basically that you cannot answer the question. So going all the way down to the axioms of set theory, so going from the real numbers and knowing how they're built as sets, going all the way down, stripping it out of the of all the clutter and seeing how it gets defined within set theory, you can analyze what that set is and what its cardinality is. And it turns out that the axioms are not enough to either prove or prove the contrary about the existence of this set X of cardinality strictly between. So this is one example of, like I said, the two facets. On the one hand, this is a foundational question because it turned out to be undecidable from the axioms. And on the other hand, it's a paradigmatic example of infinite combinatorics. We're dealing with sizes of infinite sets. Okay, so now I'm gonna start. I'm gonna switch to something much more specific, which is Ramsey theory. And well, Ramsey theory is a subject that's, I think it's famous. It's studied by many people, especially in finite combinatorics, people who do graph theory. There's a bunch of people working on Ramsey theory, and they work primarily on the finitary aspect of Ramsey theory. So they're dealing with the combinatorics of finite structures. However, there's also a very fruitful study of the analogs of all these theorems results in theory in the context of uncountable or of infinite objects, infinite structures. And this is done within set theory. So this is a line of research that I've been very involved in the past few years. And so this is something I'd like to present. The motto of Ramsey theory is that there's no such thing as total chaos. This needs to be explained. What do we mean by total chaos? And so I think I'm going to start by showing you what I consider to be the easiest result in Ramsey theory, or the very first result in Ramsey theory to me is just the pigeonhole principle. So it says that if you partition a set, I'm not saying it here, but every time I write unions for this talk, we're going to assume that the unions are disjoint. So you're basically partitioning the set X into n pieces, n cells. And well, if the set has more elements than the number of cells, then one of the cells has at least 2 elements. This is a very simple principle. We all learn it well, at the beginning of our studies, undergraduate studies, if not earlier. And well, so in this case, what we need to understand is we're thinking of chaos as, so I'm partitioning my set, and if no 2 elements have anything in common, and in this case, this is conceptualized by the partition. So if there are no 2 elements of the set in the same cell of the partition, we're thinking that this is a chaotic arrangement. And this theorem tells us that there's a limitation on that. Once the set gets too big, it's impossible to keep it completely chaotic. There's a specific size, in this case, bigger than n, that ensures that there won't be total chaos in this arrangement because there will be at least 2 elements that have something in common that are in the same piece of the partition. More generally, I'm going to make a small change in this theorem. So all I did is put in a k, another parameter k. So if you give me a k, and you define chaos as having, not having k or more elements have something in common, so not having k or more elements within the same cell of the partition. If you define chaos that way, you have this theorem, this Ramsey theoretic result in the same flavor. It says at some point, if your set gets large enough, you're gonna lose chaos and you're gonna have some order. So in this case, if your set has any size bigger than nk, then you can ensure that at least k elements will be in the same cell of the partition. Okay, so this looks very simple-minded, but I think it really is what is at the bottom of Ramsey theory. There's many other Ramsey theoretic results. I think they are all just more complicated incarnations of principles similar to this one. And I'm going to start by showing you a small example, which I always dub the party theorem. And it says if there are at least 6 attendees to a party, one can find either 3 of them that mutually know each other or 3 that mutually do not know each other. So what's happening here is I'm not partitioning. So I'm thinking of a party is a bunch of people, but we can think abstractly. This is just a graph. We have a bunch of vertices, and we have edges that relate these vertices. We can think of a complete graph because in any 2 vertices, there's an edge. And what we're going to do is partition not the vertices, but the edges. So this has some sort of 2-dimensional quality to it. You partition the set of edges. And of course, if there's enough edges by the pigeonhole principle, there will be many edges that belong to the same piece of the partition. But what we're asserting here in this theorem is more than that. It's not just that there's, well, in this case, 3 people. So here are my edges, and then 3 people would be you find 3 vertices, such that all the edges between them. So we're partitioning the edges according to whether or not the people know each other or not. And so the theorem is saying that you can find 3 vertices such that all edges between them are of the same type. Either all of them correspond to people who know each other, or all of them correspond to people who don't know each other. So it's not just finding a bunch of edges that have something in common. It's finding a few vertices such that all edges between them have that something in common. And so that, as such, that is a much stronger theorem than just the pigeonhole principle. And well, since I think that every talk, even if it's an overview like this, not for specialists, it's still good if every talk contains at least one proof. So let me at least try to prove this theorem. So what we're going to do is I have here my picture of 6 edges. Sorry, 6 vertices. I'm imagining the edges, but I haven't painted them yet. So between any 2 of these vertices, there's an edge. And I'm going to think that the edge is colored with color red if the 2 people know each other, and color blue if the 2 people don't know each other. So what we're basically saying is no matter how I configure these 2 colors, I'm going to be able to find a triangle that's either all red or all blue. So to prove this, I just pick an arbitrary vertex. And I think of all the edges connecting this vertex to the remaining 5. So I'm going to have 5 edges. Each of them is either red or blue. So, well, by the pigeonhole principle, one of the two colors appears at least 3 times. So like either 3 of these edges are at least are red or 3 of these edges are blue. So I'm going to assume that 3 of these edges are red. If they were blue, the proof would be symmetric. So the point is there's at least 3 edges of the same color. And now what I'm going to do is look at these 3 vertices that we have on top, painted solid black. Those 3 vertices, basically there's 2 cases. Either one of the edges between these 3 is red. And you can see if one of these is red, for example, let's say, I don't have a pointer, but I don't know if I can annotate here. Well, okay, let's just, I don't think I can paint over the screen, but let's just say we have, we take the top vertex, the one that's at the very top. Oh, you can see my pointer, actually. I'm seeing it. So you take this vertex and this one, and if that edge between these two happens to be red, I'm done. That's my red triangle. And the same happens, for example, with this edge and that edge. If any of those happens to be red, I'm done and I just found my red triangle. So the difficult case should be when none of these 3 things happen and all of those 3 edges are blue. But if that's the case, I just found myself a blue triangle. So one way or another, I can find a triangle, what we call a monochromatic triangle. I can't guarantee that it's going to be one color or the other, but I can guarantee that for one of these 2 colors, this is going to exist. All right, so well, this is there's a bunch of other edges that I never considered because they don't play a role in this proof. So this is an example, I think the first non-trivial example of a Ramsey theoretic result. So, well, the pigeonhole is the simplest one to illustrate what's the philosophy behind it, but this is the first non-trivial one, I think. And it shows this quality. So in this case, the magical number is 6. You define chaos as not having monochromatic triangles. And the theorem says, well, if your graph has 6 or more vertices, if it's large enough, then you can't have that total chaos. You're eventually going to have some order, going to have to find some order, namely a monochromatic triangle. Okay, so in general, Ramsey's theorem is not just for triangles, but we have for every n and k, here n is gonna be, well, in the previous example, n was equal to 3 because we wanted to find a triangle. So n is gonna be the number of vertices that we want to have all of the edges between them in the same cell of the partition. K is gonna be the number of partitions, the number of cells of a partition. And so with these 2 parameters, this depends on n and k, but there always exists a number, a sufficiently large number, n, well, capital N, such that, same thing as before, but more general, whenever you partition, this set is the edges of the complete graph with n vertices, right? So in the previous example, uppercase n was equal to 6, and we were partitioning in 2 pieces the edges of the complete graph of on 6 vertices. So in this case, it's well, complete graph on n vertices. You partition, well, you can think of it as the edges of a complete graph, or you can think of it as this, which is a theoretic notation, the set of subsets of this collection that have 2 elements. So it's picking 2 elements out of the numbers 1, 2, 3, all the way to n. And whenever you partition this in k cells and k pieces, there's going to be a lowercase n, so a set of vertices with at least n elements, such that all edges between those vertices fall in the same piece of the partition. So in this case, I'm saying this again is the same notation. The set of subsets of size 2 of the set X. So all possible edges between, if you're thinking about graphs, this would be the induced subgraph induced by the set X. And all of that graph, all of the edges there have the same color or are in the same piece of the partition. So this is a generalization of what I just told you before. So the previous theorem was n equals 3, k equals 2, but really for each finite n and k, this is a theorem. And it's a really interesting, but also really hard question to figure out, depending on n and k, what would be the optimal uppercase n that you need. It's known exactly for a few case. It's a number that grows very quickly, very fast, and for which already at n equals 7 or 8, we don't know the exact value. We just have bounds, but they're very coarse bounds. And basically, there's no hope of solving this in the short term. But anyway, at least the theorem that guarantees existence is, well, is a theorem. And since I'm focusing on infinitary stuff, I thought I'd mention the infinite version of Ramsey's theorem, which was also proved by Ramsey. I mean, in fact, the story of this is that Ramsey proved the infinite version. As a lemma, he was really thinking about some specific problem in mathematical logic, the Heinmans problem, whatever that is. But Ramsey was thinking about that problem, and he solved a particular case of it. And this infinite theorem was a lemma for that. And then the finite version was stated as a corollary of the infinite one. So, well, in any case, proved also an infinite version of this, and it says for each k. So there's no longer, it's infinite. So I want an infinite subgraph, which is not chaotic, but I can still say for each k, because k is going to be the number of cells in my partition or the number of colors in my coloring. And so this time it's whenever I partition, depends on how you want to think of it, either the edges of a complete graph with Aleph 0 elements, or simply all the subsets of the natural numbers with 2 elements. So all possible pairs of natural numbers where the order doesn't matter. So you partition this into k cells, and you will always be able to find an infinite set of vertices such that the corresponding induced subgraph has all edges within the same cell of the partition. All right. So, well, for a set theorist, it makes sense to try to see how much more you can study this. For example, there's two questions that arise naturally when you're thinking about stepping this up to the infinite realm. One of them is an analog of this. So suppose instead of n, you have an infinite cardinal. Is it still true that you can always find a sufficiently large infinite cardinal, possibly larger than the first one, that satisfies the analog of this? So that's one question. And another is, there's this strange phenomenon here on this infinitary theorem, which is that the graph is not larger than the monochromatic subgraph, right? So we start with a graph that is countably infinite, and we obtain another countably infinite subgraph with all edges within the same cell of the partition. So it's a strange phenomenon that doesn't happen in the finite realm, where you can have a graph, and no matter how you partition its edges, you can find a subgraph of the same cardinality that has that has all edges in the same piece of the partition. So these are two questions that one can ask, and they both have an answer. The first one is known as the Erdes theorem. And so it's exactly the analog of what was here in this slide of this result. So this time I have, for each infinite cardinal, it's the desired size of a monochromatic subgraph, and each n, which is the number of colors or number of pieces in the partition. You can always find a sufficiently large cardinal, lambda, which will also be infinite and strictly larger than kappa, with that property, with the property that whenever you partition the edges of a complete graph in lambda vertices and cells, you're always going to be able to find a set of kappa vertices such that the induced subgraph has all edges in the same piece of the partition. So this is directly the analog of the finitary Ramsey's theorem in the infinitary realm. In fact, the infinite behaves a little bit, I don't know, it's a little bit better behaved in this case, because unlike the previous case where finding the optimal lambda is a very, very much open problem. In this case, we have more or less the sharp bound, and we know that basically you have to take lambda equals to this. This means, so 2 to the kappa means the cardinality of the power set of some set of size kappa. So you're taking power set, and then this plus just means take the successor of that. So the least cardinal that's strictly larger than that. And this is basically optimal. So we know that you can't get away with any lambda smaller than this amount. Now, on the other hand, the other question about, if I go back a little, about Aleph 0, that has this weird property that you can partition a graph and get a monochromatic subgraph of the same cardinality. You can also wonder about that. And well, here's an example. For that question, the answer is typically you're not going to have such a theorem even on larger cardinals. So it's something very specific about the cardinal Aleph 0, and bigger infinite cardinals typically don't satisfy this property. And well, this is the easiest way to prove that. It's a theorem of Sherpinski. And in this case, it's talking about the cardinality of the real numbers. So Sherpinski finds a partition of, well, depends on how you want to think about it, either all pairs of real numbers or all edges on a complete graph with as many vertices as the set of reals. And you can partition this in 2 pieces. You don't need too many pieces, just 2, in such a way that any uncountable set, when you look at the induced subgraph, it will have edges in both pieces of the partition. In particular, the edges cannot be contained within one of the pieces because there's always edges in the other piece and vice versa. So this is a negative result. It's the same thing that happens for Aleph 0 in the infinitary Ramsey theorem. It's false for larger cardinals, in this case for the cardinality of the real numbers. It's impossible to get a monochromatic subgraph of the same size. But well, this is just the simplest example. This is really a theorem for many, many other cardinals. Well, I don't think there's, well, I don't want to risk it. So I don't think there's time to explain with detail the proof of this. But the basic idea is pick a well order for the real line. So it's one of the axioms of set theory that you can basically do this. A well order is not going to be, it's not going to have anything to do with the usual order that you think about. It's typically going to be something completely different. It's not going to respect addition or multiplication. It's not going to be useful for anything except for combinatorial purposes. And this is what happens here. So you pick a well order. And then basically, if you give me 2 reals, I'm just going to wonder whether the usual order in the reals agrees with this well order that I picked or not. So whether x is less than y both in the well order and the usual order, or on the contrary, x is less than y in one of these 2, but bigger than y in the other. And that gives me the partition. And it's a really nice exercise that uses a little bit of topology to prove that with this partition, the property that is stated here is true. Okay. So, well, the real number, the cardinality of the real numbers is, it is something well defined, but it's something that from the axioms of set theory, because of what I told you much earlier, it's impossible to know exactly which of the alephs this is. And therefore, it's impossible to get much more information than this. But if you think about specific alephs, you can have much more information. And so an example of this theorem is, an example of this is this theorem of Todorchevich, which what he does is he now looks at a set of cardinality Aleph 1. This is the first uncountable cardinal. It's just defined as the least cardinality that is strictly bigger than Aleph 0, than the cardinality of the natural numbers. Well, Cantor's theorem tells us that the cardinality of the reals is bigger than or equal to this one, but we cannot know if it's exactly equal by Cohen and Gödel's theorem. But in any case, when you take this cardinal, you take a complete graph with that many vertices and you partition the edges, well, not only is it false to have that you're going to have large monochromatic subgraphs, but even more, so you can have a partition into Aleph 1 pieces such that any uncountable set of vertices will not only not be contained in one of the pieces, but will in fact have to intersect all of the pieces of the partition. So this is, if you think in terms of coloring, this is sometimes known as called as a rainbow coloring, because basically any set that is large enough will have to show you all the colors, all the possible colors. So this is not only a negation of what would be the analog of Ramsey's theorem, but it's a very, very strong negation. This is sometimes known as anti-Ramsey theory and anti-Ramsey theoretic results. And it's typically what happens when you try to state analogs of finitary results in the infinite realm. Typically what happens is sometimes there's a generalization for Aleph 0, sometimes not, but on larger cardinals, typically what happens is the analog theorem would fails, and not only that, but it typically fails very badly. So this is an example of that. And this is not just about Aleph 1, and many, many infinite cardinals have this property, but saying which ones would, well, there's a lot of language cardinals have an analogous property to this one, but at least I show you the example for Aleph 1. All right, so I'm still gonna be talking about Ramsey theory, but I'm gonna switch a little and I'm gonna start mentioning other flavor of Ramsey theoretic results that are not so much purely combinatorial, but that also involve additive, the additive property, the operation of addition. So this is what's known as additive combinatorics, and a nice example of this is Schroers' theorem. So it says that if you partition the set of natural numbers, notice how this time I'm not partitioning pairs. I'm not thinking about graphs and edges. I'm just directly partitioning the set of natural numbers. Each natural number belongs to one of these k possibilities. Each natural number is assigned one of these possible k colors. And then no matter how I do that, I'm always going to be able to find two distinct natural numbers such that this structure is monochromatic. We have all these elements within the same cell of the partition. We have x and y. And of course, if I was only thinking about x and y, this would be trivial by the pigeonhole principle. But what is really strong here is that not only x and y, but also their sum, right? So this is an example very clear of what we mean when we say, well, this is Ramsey theory with additive combinatorics. So you're thinking of Ramsey theoretic results that tell you that you can always find certain kinds of structure within one cell of the partition, no matter what the partition is. But the structure this time is not just all edges coming from a certain set of vertices. It's this additive substructure, which is, well, it's sort of like you can have this for subgroups or sub-semigroups of the natural numbers, but this is like as close as you can get. So you have two elements and their sum. Another example of this kind of result, well, I have a remark here. This was originally used to show that one can't hope to prove Fermat's last theorem. So this was, Schroers' theorem is, I don't have the exact date, but it must be like 1912 or such. And so this is obviously way before Fermat's last theorem was a theorem. And so at that point, because this is this is something that people could think is a valid approach. It's very naive, but well, what if it works? It's so any of you who have ever trained people to participate in math Olympiads probably know this. It's a very standard. You have a problem, you want to prove that certain equation doesn't have solutions. What you do is you move all the equation modulo certain n, and then modulo n, you just have finitely many cases to test because all the numbers involved in the equation might be 0, 1, 2, 3, or all the way to n minus 1. But that's it. And so if you test all these possible values and find that none of them match the equation, then you can conclude that the equation has no solutions. So you could naively think that maybe Fermat's last theorem can be proved like this. So you want to show that x to the n plus y to the n equals z to the n does not have integer solutions. Maybe you go modulo some large enough prime p and show that no combination matches. and Schroer basically came up with this theorem to show that that approach has not hope of working, because basically when you go modulo p, what you're doing is you're partitioning n. You're partitioning the natural numbers into those that are congruent to 0, those that are congruent to 1, 2, 3, and so on, all the way to p minus 1 modulo p. And well, there's a trick that it's sufficiently involved that I won't explain it here, but there's a trick for going from x to the n. But basically, this is showing that you're always going to be able to find this combination, which in Schroer's theorem translates to there's some x to the n, y to the n, and this sum can be thought of as some z to the n. And you can always find all of those that are congruent modulo p. So there's no hope of ruling out solutions to Fermat's equation just going modulo something. So that this was the original motivation. But of course, later on, well, set theorists can ruin everything. So we just took the abstract theorem, the abstract principle, and started thinking about the combinatorics of it and how it can be generalized. Another theorem in the same vein is van der Waerten's. So same setup, no matter how you partition the set of natural numbers, as long as it's finitely many pieces. If you give me your favorite L, I can find, and basically what I can find is a monochromatic arithmetic progression of length L. So, well, this is the formal statement. You can find A and B such that this set, this is the arithmetic progression, A plus B, A plus 2. It's an arithmetic progression that starts at A and has difference B and has length L, or L plus 1, I guess, in this case formally, but that's a minor thing. And you can find the whole arithmetic progression within the same cell of the partition. So this is another kind of Ramsey theoretic result. No matter how you color this structure, you're going to find interesting substructures within one cell of the partition, interesting substructures that have only one color. Okay, and that's it. Well, this is another example. Okay, so Schroer's theorem, like I said, was eventually taken by people doing combinatorics and set theory and tried to be generalized. And so this is a generalization. It's known as the Folkman-Rado-Sanders theorem, which because it was proved by Folkman, Rado, and Sanders. But the interesting thing is that it was proved independently by each of these three, more or less at the same time. And well, so they just came up with it independently. And so this says given n and k, there's a sufficiently large n, so very similar to Ramsey's theorem, such that if you partition the numbers from 1 to uppercase n in k pieces, you're going to find lowercase n many of them, such that all possible ways of adding them together fall in the same piece of the partition. So like I said before, this is, so obviously for n equals 2, you just get x and y, two elements, and then this set becomes x, a sum with one summand, y, another sum with one summand, and x plus y, and that's it. So it's all possible sums that you can form with the elements, as long as you don't repeat the elements, and it, well, any number of summands from 1 to n. For example, for n equals 3, you get just to illustrate this, what you would get is that no matter how you partition the set of natural numbers, you can get these three elements such that all of these sums that you can form with those three elements with no repetitions fall in the same piece of the partition. All right. So the infinite generalization of this is known as Heinmans theorem. And it says, just like Ramsey's theorem, you have the infinite version and the finite one. In this case, it's the exact same. Heinmans theorem is just the infinite version of the Folkman-Rado-Sanders. And so it's just the exact analog, but for coloring infinitely many things, in this case, the whole set of natural numbers, you partition it into k pieces, and you can always find infinitely many elements, x1, x2, x3, and so on. This list never ends, such that what's known as the set of finite sums, which is precisely all possible sums that you can form with these elements with no repetitions. I mean, the finite is sort of redundant because you have no concept of a limit here, so it doesn't make sense. It wouldn't make sense to add infinitely many things. But okay, all sums that you can form with finitely many elements, no repetitions, fall in the same piece of the partition. All right, so well, this is very nice and dandy, but we don't know if we wanted to generalize this, it's not clear to what. So we want to color instead of the natural numbers some uncountable structure. But what kind of uncountable structure? Well, one obvious option would be the reals, right? So maybe there's a theorem like this where you color the reals, and well, you can go much more general than that. So what I call the generalized Heinmans theorem is just that any infinite abelian group, every time you partition it into finitely many pieces, you're going to find infinitely many elements of the group such that all of their finite sums are in the same piece of the partition. And once you state it like this, it's very clear what should be the analog of this when you try to figure out if there's theorems for these with larger cardinalities. So you would try to make G maybe uncountable, and maybe you would try to get X to be uncountable. Maybe X, you want X to have some size, some cardinal kappa, and you can tell that there's a sufficiently large lambda such that every group of that cardinality and so on and so forth. But it turns out that that's false. In fact, if G is an uncountable abelian group, you can always color it or partition it in just two pieces, and that's enough, so that it's impossible to get a set of finite sums to be monochromatic. Any uncountable set, the finite sums are going to have elements in both colors. The attribution here is because this has a very funny story. So it has my name on it. I think I proved this in 2015. And not only did I prove it, but I published it. And not only did I publish it, but people started citing it. But some years later, in fact, this is fairly recent, it's probably last year, one of my co-authors discovered an old paper of Protasov from 94 or so, where he proves the same theorem. It's just the paper had been forgotten. And then later on, another of my co-authors found an even older paper of Malichin. This is from the 60s probably, where he proves the same theorem. It's just that the paper got forgotten. So, so this is a theorem. I think this is evidence that the theorem is very natural. And also, I'm happy to publicize it as much as I can to prevent people from forgetting it again and then having a few years from now someone else prove it independently once again. But anyway, okay, so I don't know. This is 3 people independently proved it. I guess by date this should be just attributed to Malichin, but well, there's this story about this. And it shows that the uncountable analog of Heinmans' theorem has to be false. And even more, it has to be very false. So in a follow-up paper with Asaf Rinot, which is he's a researcher at Bar Ilan University in Israel, we prove something even stronger. So not only can you partition here in 2 pieces, but you can partition incountably many pieces. So any uncountable abelian group has a countable partition such that every uncountable subset, when you look at the finite sums, that has to contain elements from all possible pieces of the partition. So it's again an example of a rainbow coloring. You're coloring with countably many elements, and every finite sum set which is sufficiently large has to have all possible colors represented in it. And another theorem, I mean, well, we have a paper, actually the results must be from like 2015 or so, but 2017 is the date on which the paper appeared published. So we have a bunch of results in the same vein in that paper. And just to give an example, analogous to Todorcevich's theorem for graphs, we have this theorem for groups where any group of cardinality Aleph1, you can obtain a rainbow coloring of size Aleph1. So a partition into Aleph1 many colors or Aleph1 many pieces, such that any uncountable set, its finite sums will have to hit all possible colors. And once again, this is not exclusive of Aleph1, and there's a great variety of infinite cardinals that satisfy the analog of this. Just replace Aleph1 with kappa. But obviously, I don't have time to, and well, I don't think even makes sense for this kind of talk to try to even define the technical condition that these cardinals need to satisfy. All right, so just, to close my talk, I would like to mention a few open questions. This is not by no means an exhaustive list. It's it's not even a representative list because I didn't pull problems from different, different flavors of Ramsey theory. I just grabbed a few questions that currently interest me, and they're still in the realm of finitary combinatorics. And one of them is Owings's question, or maybe I should have said Owings's problem. I think that's the official name of this. And it's asking whether there's this kind of Ramsey theoretic result. Is it true that whenever you partition the natural numbers in two pieces, you can find an infinite set such that its sum set is all contained within the same piece of the partition? So the sum set is this. And so as you can, well, if you think a little bit about it, you see that this is really a set that contains elements of two types. On the one hand, the x plus y's, where x and y are distinct elements of x, of the set x. But on the other hand, it also contains things of the form 2 times some element of x, because if x is equal to y, that's what you get. So it has these two kinds of elements, which is what makes this problem difficult. And this is an open question, and it's been open since the 70s, I think 1970 or 74 or some such. What's funny is that the question that is open, I mean, its openness relies heavily on having a partition into two pieces. Because if I were to partition into three pieces, we already know what happens. We know that the answer is no. And this is a theorem, this is not Heinmans' theorem, but it's also a theorem that was proved by Heinman. And he shows that you can partition the natural numbers into three pieces in such a way that no infinite set of this form can possibly be contained within one piece. So it's a Ramsey theoretic result that we know is false for three colors, but it's been open for a really long time whether this holds for two colors. And so I consider this to be a very interesting problem. And then people have also turned to look at uncountable or infinite, well, this is infinite, but uncountable versions of this. So given a semi-group, typically a group, but every now and then a commutative cancellative semi-group will do, like the case of the natural numbers, you can define h of g as the least k such that the corresponding Ramsey theoretic result fails, such that there's a partition with k pieces. This is, okay, I made a mistake here. I don't mean to say that this is a rainbow coloring, just that it's a bad coloring. So it's not necessarily true that x plus x intersects all of the AIs, but it intersects at least two. So it's impossible for it to be contained within just one of the AIs. So it's the least k such that the corresponding Ramsey theoretic result fails for a partition into k pieces. So for example, in the case of the natural numbers, we know that this is either 2 or 3. Right? So it could be 3 because we already know that the theorem fails for 3 colors, but we don't know if it fails or it holds for 2 colors. So the number can be 2 or 3. We don't know the exact value. And Owings' questions, answering that question would give us the exact value of h of n. In the case of the real numbers, it is known that h of r is bigger than 2. So this is really interesting. It is a theorem that if I write exactly what is written here, but put the set of real numbers instead of natural numbers, then this is true. And this is a very recent result as well. It must be from 2018 or so for the real line. And also shortly before, it had been proved that there's large enough finite values such that the question for that number of pieces of the partition is undecidable from the axioms. So h of r can be infinite, or it can be some finite number of the order of 2 to the 2 to the n or some such. But still, you can ask, well, so at some point it becomes undecidable, but what is the largest number such that this is decidable and true? So what is the largest k such that you can prove this, right? So we know k equals 2 at least works, but what about k equals 3, for example? So this is a really nice question, and obviously you can also vary the question to take simplified versions of it in the hopes of making progress. For example, adding additional assumptions to the usual axioms of set theory. For example, a nice question that's stated in one paper that deals on this subject is whether assuming that there's a real valued measurable cardinal, whatever that means, implies that h of r is infinite. So if you can't answer these directly, you might want to add some of the things that we know are consistent with the rest of the axioms, but and try to see if as a consequence of that, I can get some more precise information. All right. And so with this, I'd like to finish. I thank you all for your attention, and I'm happy to answer any questions you have now.